The concepts of force and Newton's laws are actually pretty foundational to what we're actually doing this term. This is one of the signature topics. Newton's laws are one of these small number of subjects that you should carry out into your life that talk about some understanding of how the physical world works. So in our last unit on kinematics, we learned about velocity and position and acceleration and how all of these quantities are related to each other through time. And we found that if we knew what a time-dependent functional form of acceleration was, then yeah, we could find velocities as a function of time, and we could find positions as a function of time, and we could see how the whole system evolves. But where does the acceleration come from? What makes it? How do we create accelerations? And that's really what this unit is about. Because the way that we make accelerations is by using forces. And whole combinations of forces are what lead to accelerations on certain kinds of objects. So as we get going, the first thing that I would like to look at are what are these forces? What are kinds of forces that we are going to be able to use? And we already have some sense, probably, of what a force is. It's some kind of a push or some kind of a pull. I've tied a string to something, so I yank on it. That's something that gives a force. And while there are other ways to get forces, it's basically an interaction between two objects. I can pull on some block, and the block is actually putting some influence on me. I can push on a wall, but the wall is supporting me in such a way that I'm not pushing my way through it. So a force is really an interaction between two things. Force is a vector quantity because given some object, whether I'm pushing to the right or pushing to the left on that object, I really see the difference in that kind of an influence. So pushing and pulling are both force vector quantities, giving me some influence in a way to manipulate an object in a particular direction. Now there's a small subset of forces that we deal with in this class. This is not an extensive list of all of the possible forces, but one of the forces that we're going to work with is something called a normal force. This is a force of interaction between an object and any surface that it is in contact with. So for example, I could have a copy of our textbook and I could put a coffee cup on this textbook. So there is a normal force that this book is putting on this coffee cup. And it's going to be a force that may change as a function of orientation. The force that the book can put on some object, the force that a surface can put on some object, can only be applied perpendicular to that surface. So what we see down here, the normal force is the force that a surface puts on an object. The direction is always perpendicular to the surface. So when you talk about normal forces, a normal force is a force of a surface on an object, and it is normal to the surface. That's why it is called the normal. Another force that we're going to see later is some frictional force. And we have a little feeling for how this works, but it turns out that there are some counterintuitive things. For example, we might think that, well, a frictional force is just going to slow things down, right? Not exactly. Not exactly. Because it turns out if there wasn't friction, you wouldn't be able to move. You need to have some frictional force in order to speed up as well. So frictional forces can be used to speed you up. Frictional forces can be used to slow you down, depending upon how they're being used. So we're going to talk a little bit about frictional forces and different types of frictional forces. And it turns out that the frictional force on some object is proportional to the normal force. The bigger the normal force, the bigger the frictional force. But the direction of the frictional force is not in the direction of the normal force. So we see from this picture here that the frictional force is parallel to the surface. It is proportional to the normal force, but it is in a different direction. And this frictional force is going to be applied opposite the direction of motion, at least the way as it's pictured here. We're going to talk more about friction later on in this unit, in this module. Another force that we may concern ourselves with is a tension force. This is something that's applied when we're pulling on some string. Now with a string, you can't really push. You push on a string, the string goes limp and it doesn't do anything. But I can pull on strings, and that's what we mean by a tension force. If tension goes to 0, that just means that your string has gone lax and you're not doing anything. But a positive tension means that there's really tension in this string. And finally, weight is another one of these forces that we deal with. Weight is a force. It's a special kind of force. It is the force of attraction of an object to the earth. So the weight force is how much force the earth is using to bring objects down to itself. That gravitational acceleration, little g, gravitational acceleration of the earth, this is something that influences the motion of some object. So I let some object, whether it's a ball or whatever, I drop it. I can have some ball and I drop it. We saw that it accelerated. Why does it accelerate? It accelerates because of a force influence coming from the earth. This ball is attracted to the earth, and the force of that attraction is what draws the ball to it. So this actually relates a couple of quantities, because here in the States, if we were to look at the size of some person, maybe they're doing dieting or maybe they're an athlete of some kind, and we want to figure out how big somebody is, and they get on a scale, the scale is saying how big somebody is in pounds, at least here in the US. You know, but this is a force. And force is not always going to be the same depending upon where we are. What we really should be keeping track of is mass. Mass and force are not the same thing. Mass is a scalar quantity. Force is a vector quantity. They don't have the same units. They're not the same nature of an object. They're not really the same. But force is a special, the weight is a special force. It is the force of attraction of an object to the earth. And it's always illustrated in this particular way. It's a vector quantity. Weight is a vector quantity. It's always a quantity that is down in that nature. Now, force, as we've been describing here, all of these forces are vector quantities. And we've already talked about vectors. We can break vector quantities up into various components if we want to. So here, maybe I'm pulling on some string with a force F. There could be an X component of that force. There can be a Y component of that force. And resolving these two forces that are along cardinal directions, like X and Y, might be an easier way for us to work with forces. Working with perpendicular and parallel components of forces are very, very common. Similarly, force does not have to have any position. If we wanted to handle force as a pushing phenomena, we wanted to handle force as a pulling phenomena, that's all fine. Vector quantities don't have position. They only have magnitude and direction. All of these forces add just like vectors, and we can resolve them in the typical ways that we worked with vectors in the past. Okay. Now, why do I talk about all this stuff with forces? Because forces are what Newton's laws are all about, his 3 laws of motion. Now, these came about right around 1700 or so. So they've been around for a while. But when Newton was looking at the world and coming up with these 3 laws of motion, it was a true stroke of genius, a true stroke of insight, because he was looking at the world and he did not see the world as the world saw things progressing. So let's look at some of his laws, and then we'll talk a little bit about why they were so insightful, why they're so genius, and why we talk about Newton to this day. Because these topics, these 3 laws of motion, are what Physics 1 is all about. It's all built on these laws of motion. So what are these laws of motion? There's 3 of them. His first law of motion is commonly called the law of inertia. A body acted on by no net force moves with constant velocity, which may be 0, and 0 acceleration. So it has this word force that is new. It just showed up for us in this video. We didn't talk about forces before. We know about constant velocities, but I don't know what this force is. And this is a law that's looking at a condition of no force. Okay, so if I don't know what a force is, how do I know when there's no force? Okay. Another possible way to talk about this might be that in the absence of external forces, and when viewed from an inertial reference frame, an object at rest remains at rest, an object in motion continues in motion with constant velocity. Okay, so this is still talking about no forces, and now we've added another set of terminology, an inertial reference frame. This is actually getting worse. But what this law is really talking about, and why it's called the law of inertia, is it says that some object, an object has this innate sense to it, that if it has a large amount of this quantity called inertia, it's very hard to change its state of motion. If it was zipping along in some fast straight line and it has a lot of inertia, it's going to be very difficult to divert it. If it's just sitting there and it has a large amount of this inertia, it's going to be very difficult for us to actually get it to go. And it turns out that mass is this measure of inertia. A massive object strongly resists changes to motion. So this mass quantity that we've talked about a little bit in Unit 1, we didn't talk about it so much last week, but we did talk about it in Unit 1 when dealing with measurements. Mass and weight are not the same thing, but mass and inertia are strongly related to each other. Now when I say mass and weight are not the same thing, mass is a scalar. It is an internal quantity. It's just built into the system. It is a special quantity that is handled as a fundamental unit in SI units, the kilogram. Weight is a vector. It is a force. Force is derived from multiple dimensions. Force is a kilogram meter per second squared. It's not fundamental. And in SI, it's measured in newtons. So when I say mass and weight aren't the same thing, they really are different dimensionality. They have different units. They have a different character. Mass and weight are not the same thing. Mass and weight are not the same thing. But there is a relationship between them. Now, if we wanted to see, what we just saw was a little more modern interpretation of Newton's first law. In his words, he said that every body perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. It's not clear even why he included this as a special law, because this law really is a consequence of his second law that we're going to talk about next. So what is his second law? Now, this is relating to these inertial reference frames. This was the Part D lecture of last week, where we were looking at inertial reference frames. Really, we were looking at inertial reference frames? No, we were talking about relative motion. And what's the difference between relative motion and inertial reference frame? And in that video, I talked about how two different observers could be looking at what's going on with some point P in slightly different ways. Maybe this observer at point A is at rest, and P is doing whatever it's doing. Maybe it is sitting there, maybe it is moving with constant velocity, maybe it's accelerating. I don't know. But if it's accelerating, it has constant acceleration. That's the biggest the acceleration could possibly be for point P. And maybe we have some other observer at point B, but point B is moving. They're in some car, or they're in some train that's moving at a constant velocity. And if they're looking at point P, they may see some different things. So point A and point B can both look at point P, but if there is some relative motion between B and A, then A and B are not going to see P exactly the same way. And so we went through this whole process of figuring out how would these two different observers find point P, how would these two different observers see differences in velocity, and how would these two different observers see differences in acceleration. And one thing that we found is that as long as point B was moving at a constant velocity, zero acceleration, then both observer A and observer B would see the same acceleration for point P. They would both see the same acceleration for point P as long as VB was only moving at constant velocity. So we've talked a little bit about this constant velocity thing before. We just saw that in Newton's first law. And it turns out that now we see a little bit about this acceleration parameter here. You are in a frame of reference where you can talk about Newton's laws. We don't know what force is yet, or the relationship between force and acceleration, but we find out that we will be good judges of Newton's laws if we are in something called an inertial reference frame. What is an inertial reference frame? A reference frame that does not accelerate. We can be in observer A, or we can be observer B, and we're all going to agree on the acceleration of point P as long as point B does not accelerate. It can have a constant velocity, it can't accelerate. And if that is true, B only has a constant velocity, everybody agrees on what the acceleration of point P is. So if you are in some reference frame that's not accelerating, that is called an inertial reference frame. That's what we're talking about. Okay, so there's this relationship from what we saw in the past with relative motion and how we observe the accelerations of objects. And we were looking at cases before where there's no net force and the object isn't allowed to accelerate. That's what constant velocity means. So what happens if there is a force? What kinds of accelerations are going to be at play? And that's what Newton's second law is about. His second law is what happens if we do have force, when force is not equal to zero. One way to say his second law is that if a net external force acts on a body, the body accelerates. The direction of acceleration is the same as the direction of the net force. The mass of the body times the acceleration of the body equals the net force vector. Lots of forces can work on some object. And when you look at all of those forces and how they vectorially sum with each other, that will tell you the direction of acceleration. The net force is going to be proportional to the acceleration of the object. Another common definition given in the books is that when viewed from an inertial reference frame that we just talked about on the previous page, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass. This is a whole lot of words. What are these words saying? These words are saying that the net force on some object is equal to mass times acceleration. This net force is the vector sum of all forces on some object. Okay, so once again, we can get out our coffee cup and our book. So I get out my book, I get out my coffee cup. So my coffee cup is going to be the object in question. Are there forces acting on it? Sure. There is a force, a weight force on this because it is attracted to the earth. I know if I was to drop it, it would fall and break. So it is attracted to the earth and it has some weight. But it's sitting on a book. And the book is putting a force up on it. So this object has two forces that are acting on it. And I don't see it accelerating. So because it's not accelerating, the vector sum of those two forces on the object must balance. The vector sum of the forces is equal to zero. And that's why we don't have any acceleration. That's fine. So is there any condition where we could have forces working on this object and not see zero acceleration? That would be looking at the object without the book. If I was to drop it now, the only force acting on it would be its force of attraction to the earth. it would fall to the earth and it would break. It would certainly accelerate, and it would accelerate at a magnitude of little g. That's what would happen to it. So it would have unbalanced forces. The unbalanced forces would lead to accelerations. Now, there's lots of problems we're going to look at. Sometimes there will only be one force. Sometimes there will be two forces. Sometimes there could be 3 or 4 or 5 or 6 or 7 or continuing on. But if I look at all of the forces that are working on some object and vectorially sum them together, that's what the net force is. And once I know the net force magnitude, if I divide by the mass of the object, that tells me the acceleration of the object. The more massive something is, the more force is needed to get a particular amount of acceleration. And that's kind of what we were talking about with Newton's first law of inertia. Something that has a lot of mass is going to take a lot of influence to change its state of motion. That's what inertia is all about. Similarly, for something that is light with very little mass, very little net force is needed to get very high accelerations. Okay. Now, there's a couple of things to keep in mind here. Force does not cause motion. Here, we just had a case of some object that's feeling not just one, it's dealing with two forces. There are two forces on this cup, but its state of motion is not changing. Force does not cause motion. Force can cause a change in motion. And even then, it's going to be related to some net force. Only net forces lead to a condition of a change in motion. Similarly, you might have often heard that Newton's second law is F equals ma, or force is equal to mass times acceleration. And that's not exactly true. Ma isn't a force. Ma gives the resultant acceleration from all forces. It's not F equals ma, because ma is not a force. F net is equal to mass times acceleration. All of the forces lead to the total acceleration of the object. So if you can look at all of the forces, then you can say all of those forces will equal mass times acceleration. That's different, but related. Finally, mass is a constant unless something happens to the object to deform it or pull a chunk off of it. So there's certainly catastrophic things that could happen, of course. But typically in this relationship, force is proportional to acceleration, and mass is a constant of proportionality. There are often conceptual problems that say, okay, well, we've got some object, and we would like to double the force on it. How does the mass change? And you look at a relationship like this, and, well, you doubled the force, and F is equal to ma. And so one thing that I could do is, well, I guess we doubled the mass, right? That's how we keep the equality. Au contraire. That's not what's going on, because force is related to the acceleration. The mass of the object stayed constant. Or let's say you were to say, well, we noticed that the acceleration of some object doubled. What happened to the mass of the object? Well, the force isn't the constant. Mass is the constant. Mass is the thing that we can pull off the shelf. And it might have printed on it what the mass of the object is. It doesn't change. The mass of the object is the mass of the object. It's intrinsic to that particular object. What this law is saying is that there is a constant of proportionality between net force and acceleration. The constant of proportionality between these two things, the thing that fixes the units and makes sure all the units are consistent, is the mass. The mass is the constant between all of these quantities. So that's useful to keep in mind. Force has units of newtons. A newton is the force that is needed to make a 1 kilogram object accelerate at 1 meter per second squared. Now, what is Newton's laws in his words? His second law. A translation might say that a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. What Newton calls motion here is what today we call momentum. And we're going to discuss momentum in Module 5. And his way of writing this is incredibly insightful. It's actually more insightful than what we're talking about in this unit on force. The way he applies it to momentum is incredibly clever and incredibly modern. It actually influenced where our discussions and discoveries of relativity came from. Because of the way that he actually wrote his law, he called it motion, okay, fine, and it's really momentum, but okay, that's fine. It was very insightful what he did. Similarly, it's actually the rate of change of motion and not the change of motion itself that's proportional to force. In today's words, what it would mean is that the rate of change of motion is the time derivative of the momentum. And so there's a couple of little details here and there, but he's creating a whole branch of physics. Of course, there's going to be some weird things that might pop up. What is clear from his writing is he did understand what was going on here, and it was incredibly genius. So weight is a force, and it can lead to the net force on some object, just like we said before with this coffee cup. So how do we figure out a weight, and what's the relationship between the weight and the mass of an object? Well, if I was to drop an object, and it accelerates at the acceleration of gravity of the Earth, little g towards the Earth, I know the acceleration, and I might know the mass of that object. So apparently the weight of the object is that mass times that acceleration. It is m times little g. And it's a vector, but little g is really kind of a vector quantity. It is an acceleration toward the Earth. That's what little g is, at least in magnitude. So weight is m times g's direction. That's what it is. Okay. And because this is a vector equation, just like in projectile motion, 2D, 3D motion that we talked about in kinematics, everything can be handled in the component form if we wanted to. So say we look at all of the forces in the x direction, that's going to tell us about acceleration in the x direction. If we look at all of the forces that are in the y direction, that is what's going to tell us about acceleration in the y direction. And finally, in the z direction, if you tell me all the forces into and out of the camera here, that will tell you about the acceleration in the z direction. Sometimes some of these forces will balance. Sometimes some of these forces will not. And that's totally fine. But we can handle each of these things in its component form, working with x, y, and z independently if we wish. Now I said there are three laws of motion. What's the third law of motion? This is what we commonly call the law of interaction. So Newton's first law is saying what happens if we don't have any forces. Newton's second law is saying what kind of accelerations are created if we do have net forces. But we don't know where the forces are coming from. So how do we put a force on an object? And that's what his third law is all about. So a modern way of expressing his third law is if a body A exerts a force on body B, an action, then body B exerts a force on body A reaction. These two forces have the same magnitude but are in opposite directions. These two forces act on different bodies. Me pushing on the wall means that a wall pushes on me. My force is applied to the wall. The wall's force is applied to me. Those are different objects, but there is a relationship between them. Another way to say this is if two objects interact, the force 1,2 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force 2,1 exerted by object 2 on object 1, mathematically expressed as this. Now a main note that I would give here is a reminder that action-reaction pairs don't act on the same object. Eventually, we are going to be using something called free body diagrams to look at all the forces that are working on some object. And if an object is sitting on the table and I want to see all the forces working on the object, I don't have to worry about the force that the object is putting on the table. That's not part of the problem. I only need to look at the force that the table is putting on the object. That's the force that I have to concern myself with. So action-reaction pairs don't work on the same objects, those vector forces that show up in these future diagrams are related to each other, but they're not the same thing. Those forces only show up in one of those diagrams and not in both, except in the sense of its action-reaction pair. If I push on a table, the table pushes on me. One of those forces is on me, one of those forces is on the table. Okay? Now, while it is strongly implied, I also want to explicitly state that forces come in pairs. All forces come in pairs. The only way that we can apply a force is if it comes in a pair. That's Newton's third law. If I push on a door, the door pushes on me. If a car driving down the road hits a bug and applies a force to that bug, the bug is applying a force to that car. My weight applies a force to the floor applies a force to me. That's what force pairs are all about. It's also useful to note that weight and normal force are not an action-reaction pair. There are times that a normal force could be the weight force, but there are times when the normal force is not. Weight comes about because of an attraction to the earth. The force pair between those two objects is the earth puts a force on the object puts a force on the earth. Okay, because the earth's mass is huge, that's what means the acceleration of the earth toward that object is pretty small. From net force equals mass times acceleration, and the fact that this force of one object on the other objects, those have the same magnitudes. If mass times acceleration is equal to mass times acceleration, if one of those masses is really big, the acceleration is small. If one of those masses is smaller, the acceleration is big. And that's why when we're looking at a problem, standing from the surface of the earth, and we see the ball drop, we don't see the earth go up to the ball. That's not how we observe it. That's really kind of what's happening, but that's not really how we look at it. Okay. Yeah, so that's good stuff for this page. If we wanted to look at Newton's laws in his words, to any action there is always an opposite and equal reaction. In other words, the actions of two bodies upon each other are always equal and always opposite in direction. And really, this is a pretty modern take on what Newton's third law is all about. It's not significantly different than what we saw in the more modern terminology. Okay, so this is a good place to stop. There are a couple of example videos that I have posted in Canvas, but we're really not at the problem level yet. That's what the next video is all about. So now that we know Newton's first, second, and third law, how do we use them to solve problems? And for that, we're going to be looking at the case of something called free body diagrams. So first, we're going to take some objects, apply forces to them, and see what happens. What kind of accelerations come out? And once we know accelerations that come out, how can we look at velocities and positions as a function of time? We're going to look at two different kinds of cases. First, with no friction, and then what happens if we look at a more realistic world where there is friction. We don't know a lot about frictional forces yet, or what they come from, but we're going to look at these two different scenarios. How do I apply forces to an object, and what comes out from the acceleration and the analysis of that kind of a process. So that's going to be coming up in our next video.